And we are moving to the next presentation that is given by Volker Blum from Duke University. Hi, Volker. And he's going to talk or to tell us about how difficult or easy, I don't know, it is to deal with hybrid databases, right? So the screen is yours, Volker.
Yes, thank you. Well, first of all, thank you very much for actually having me at the conference. And second, I'm excited to see some of the live participants in Louvain. And I wish I was there. As you already said, Claudia, I'll be talking about data for hybrid perovskites. It's really a little bit broader. It's hybrid organic, inorganic semiconductors, but the data structure and also project that fuels this is called hybrid cubed. So the 3 stands for cubed and the 3 Ds stand for discovery, design, and dissemination. That will come in a moment. What we focus on really are semiconductors inspired by the hybrid perovskite paradigm. You can see one of them over here, which is actually a fairly complex object. If you look at it more closely, it has inorganic components, it has organic components, in this case, an organic oligomer of an organic semiconductor, so quarter-thiophene. But more importantly, these materials actually exist as crystalline materials. And so that's what we focus on, materials that have high crystalline quality, so they can be made with high definition as new semiconductor materials. And the key funding agency, which I'll mention, but I want to say this at the beginning, that funded this particular project is the National Science Foundation in the DEMREF project. And so we're extremely grateful to them that this happened. We also work in Center for Hybrid Organic and Inorganic Semiconductors choice that's funded by Department of Energy. And on the computational side, our work has been supported by a number of large infrastructures, or else we wouldn't be here. And then there's Springer Materials. So Springer Nature is credited down here, with whom we're also going to be working on this in the future. And so then you see my name, but it turns out there are a lot of other names involved, and I'll detail them on the next slide. So this is, before I do anything else, these are the acknowledgements of the people who really are doing the work. And so on the database, which is the narrow data focus project that I'll be highlighting in the center of the talk, amazingly, actually, some of the key work has been done by undergraduate students. So all these 6 people shown here are actually undergraduate students, and Zhao Chengdu, who came into my office 4 years ago and asked if there was a project. He really founded this database and programmed a good part of it and made sure that this continued. Becca Lau, Lily Alomari, and Yannick Eisenlohr actually helped with conceiving and pushing on some things for this talk, apart from being contributors to the database at the high level. And then many others contributed. So in my group alone, probably the most important one is Raoul Lasner, who did a lot of the infrastructure programming at the base of this. Manoj Jana is actually an experimental scientist and quite established in his own right. He comes from David Mitzi's group. And so this brings me to the overall project, which is focused on science of hybrid perovskites, which brings together 6 PIs from institutions here in the research triangle near Duke University, also UNC and NC State University. And Matt Beard, Haiping Lu have supported this from choice. And I should mention Springer Materials, because that will play a role towards the end of my talk, and Sharon George, in particular, the senior editor in Springer Materials, responsible for these things. We've worked together well, also in other contexts over the years. So let me get to the agenda. So what I'll try to speak about in the next 40 minutes or so is, well, hybrid organic, inorganic perovskites, which I'm sure many in the audience are familiar with. I'll say a few things anyway. And then the hybrid cube database, and also the MatDCube software that we've been working on to enable the database and perhaps more databases that can be built on this in the future. And then I'll give one example on where having accurate data helped us, which in this case is a structural descriptor based on octahedral bond angle differences that allow us to predict the occurrence of large spin splittings of Rashba or Dresselhaus types, or well, spin-orbit coupling mediated in chiral layered perovskites, which is a hot topic in this field today. And then in data, really, there is the other question of sustainability and what do you do in the long term. And already during my PhD, my own PhD, I found that Landau Bernstein was actually a book that I needed very often because it had high quality curated data. And that's a hard thing to obtain because it requires detailed work, and Landau Bernstein had that. And so I'm quite proud that we've been working with Springer Materials for a while on other data, and that we're also going to be working with them in the hybrid perovskites and journal perovskites area in the future. Yeah, so that's the outset. So hybrid organic inorganic semiconductors. I already had this image on my first slide. So this is lead bromide quarter-thiophene. But in general, you can think of them as materials that are made of two components, an inorganic component and an organic component. And you can tune both in different ways. So you have a number of inorganic options available, but you also have the full array of synthetic organic chemistry that can allow you to tune models. And so you could hope to make new functional materials. And so this is ongoing in this field in a rather successful approach at this stage. The key point, as I mentioned earlier, is that we're interested in materials that have a crystalline, so well-defined framework, but we can have quite complex organic functionality. And that creates the space of semiconductors we're interested in. And that entails plenty of properties. So the energy band gap is probably the most important one for any semiconductor, as well as carrier properties. So which carriers do you have? Can you dope them? Can the carriers move around? Optical characteristics are probably the leading spectroscopic quantity of interest, and also for applications, of course. But other quantities are coming in as well. So magnetic semiconductors have been of interest for a long time, but semiconductors that are not themselves magnetic, but allow for spin transport. So controlled transport of spin polarized carriers are also quite interesting. And I could go on with this list. It turns out there are a lot of properties that people are actually exploring in these semiconductors. And so there's a very rapid addition of known and prospective hybrid semiconductors going on in this field. So how did this come about? Actually, it turns out that the advent of the perovskite field as interesting semiconductors, in particular for photovoltaics, is not that new. Photovoltaics probably boosted the hybrid perovskite field to its current shape, as you'll see. But David Mitzi pointed out to me long ago, that there's a Nature paper in 1958 that talks about crystal structure and photoconductivity of cesium plumbo halides. And that already says that essentially materials of this kind, in this case cesium instead of an organic component, materials of this kind can be photoactive. And so if you look further, there is this hybrid perovskite, methyl ammonium lead X3, a lead 2 system with cubic perovskite structure. And this was characterized in this paper in 1978. And since then, the field actually grew, and many developments of organic inorganic hybrids based on this paradigm followed up to 2009 when this paper was published, which I'm sure many in the audience have heard about, which says organometal halide perovskites as visible light sensitizers for photovoltaic cells. At this point in the context of dye-sensitized solar cells, but it turns out that methyl ammonium lead iodide in particular was a good solar cell material in its own right, and then a run started, and as of yesterday, this paper has been cited 14,000 times, and this gives one a partial idea of how fast this field is actually growing. So the net result of this boost that the field got is that there's a vast increase of the number of newly synthesized hybrid compounds. There's also a vast increase of the number and type of properties being studied, and more importantly, a vast increase of literature to keep track of. And if anybody works in this field, you know that this is a challenge. But there's also an ongoing issue, of course. If you have a lot of literature, then the question is how variable is the data that's reported, and to an extent, there is actually some variability of data in the literature. And so the question is, can we capture this data volume? And that's what we set out to do a few years ago. So this is the short introduction of what this database is about. It's in principle very simple hope, which is that we can create a curated database. So one that's focused specifically on any properties of hybrid organic inorganic compounds related to the perovskite paradigm. This is a long sentence, but it gives us the flexibility and also the delineation that we need. And so again, this hybrid cube stands for hybrid design, discovery, and dissemination of such materials. And the database itself can be found at this URL here. And the way to use it is to start searching. We'll come to that in a few minutes. So what have we at this point? We actually, because this is curated and hand-entered, we have about 442 hybrid organic and inorganic compounds in the database from only a few hundred references, but going through the references and pushing through with them is an ongoing challenge. And we have 69 properties, and this, of course, is some volume that we want to increase in the future. More importantly, the experimental properties that we have in there, like atomic structure and photoluminescence in particular, or absorbance, can be quite varied. There are many others. And on the computational side, of course, things like atomic structure, band structure, and so on are the targets. But the real challenges in the field, as you know, rest upon the structural diversity, which are also the opportunities that come from the field. So there are the three-dimensional perovskites. This is the calcium titanate, so perhaps the original perovskite structure, all inorganic, which is then mimicked by methyl ammonium lead halides. So this is methyl ammonium lead iodide in the same structure. But there are also the two-dimensional perovskites, which we focused on more also in our scientific work in the HybriD3 projects, which can occur in various shapes with a van der Waals gap or without one. Then there are 2.5-dimensional perovskites, such as this one, where you have well-controlled numbers of layers of 3D perovskites wedged between molecules. That allows you to tune the band gap. You can have one-dimensional structures. So this is actually a one-dimensional structures looking along the one dimension. Or zero-dimensional perovskites, where the octahedra coming from the perovskites are actually isolated in a matrix of molecules. Or you can have something that's inspired by the perovskite paradigm. So this thing here has octahedra, but the octahedra are connected in a slightly different way. They're connected over edge and not corner. And for the people who categorize these things, that's actually a difference. And yet they're organic and inorganic hybrid semiconductors. And you can see that this gives rise to a vast space of materials that one could imagine. But the question is, can one predict things simply and also do structural subtleties make a difference? And so they do, of course, and this is why I think that it's important to do this carefully and look at data individually one by one, because it turns out structural subtleties matter. And so this comes from our own work, but I'll try to jump through this briefly, but it's really an important point. You can't just go and assume that you put the molecule in here in a predicted structure. This actually is an XRD structure. It's not predicted. It's confirmed by a prediction, but not itself predicted. But you can't just put the molecule in and hope for the best. It turns out that the electronic properties will be affected by the structural subtleties. And in our case, this is most easily seen by looking at these particular structures, which are actually quantum well structures. So you can reduce them to a quantum well model where you have band edges of an inorganic and band edges of an organic, shown here in red and blue. And that gives rise to 4 different types of quantum wells that you could look at. And the question for a given new functional material that you would like to make is, which type of quantum well is it? And we were quite successful with this initially. So you can do electronic structure calculations. Electronic structure calculations are fairly straightforward. So this shows energy bands that are derived from lead. So the inorganic bands, which lie above these, at the conduction band edge, above these black lines here. So these are the organic derived bands. These here down here are also organic derived bands. And if you do a calculation without spin orbit coupling, which was the standard in the field in the first 5 years or so, for some of the 3D perovskites, you see that this is actually an organic to organic quantum well, so type 1, this kind here. That's not true. If you actually do the calculation correctly, including spin orbit coupling, you see that the lead bands come down and you actually have a semiconductor where the electrons are on the inorganic and on the conduction bands and some inorganic conduction bands, and the holes are on the organic valence bands. And so in fact, what this really says, it's a semiconductor of this type here, which we call type 1b in this case. And that's an innocent little thing, but of course it has significant ramifications for the structure. Now in this case, that says the same thing. This is this picture again. In this case, this was actually something that we could probe further and something that already had been discussed before, at least for this amino ethyl thiophene lead iodide and chloride, where the bands shift around in different ways. So this one is also type 1b, whereas this one type 2b, whereas this one actually is almost organic to organic and should have different optical properties. And that was actually seen in a paper by David Mitzi and co-workers early on, already in 1999, except when we made the computational prediction, we didn't know that this data existed. So here you can see that there's a very strong photoluminescence line at room temperature in the chloride variant, but not in the iodide variant. So this is consistent with this assessment. Okay, so this works. And so where's the problem? Actually, the problem is here. This is a different variant of the same material. You have 2 thiophene groups instead of 4 thiophene groups. And it turns out that if you look at the crystal structure a bit more closely, which Manoj Strana did experimentally with David Mitzi's group and then with us, you get different orientations that are possible for these organic molecules. And they can be herringbone-like, or they can be all parallel stacked. And in 2 different, it turns out there's rotational disorder, actually, if you look at X-ray diffraction images of this material a little bit more closely, which is related to different layers being differently oriented. And so you can, for instance, believe in all parallel stacking, or you can believe in herringbone stacking of different types. And it turns out that the energy band structures that come out of this kind of exercise look subtly different. This, in fact, here is an inorganic to organic quantum well. This is an inorganic to inorganic quantum well. So the optical properties should be quite different. And that's shown here as well. And so if you look at total energies, you see that total energies per atom are actually noticeably different in this case. But if you don't know that, you would be predicting the wrong quantum well type. And so the detailed orientation of these molecules actually matters, and the correct quantum well type is this here, which is actually optically active. All right, so that's one challenge that came from our own work. This is something else that comes directly from the database that Zhao Chen put together a while ago. We looked at phase transition temperatures as another example, in this case, the orthorhombic to tetragonal phase transition in MAPI. And this is sort of the grandmother of all phase transitions, I would say, in these materials. That should be very well studied. And yet it turns out that there's a fairly large variety of values for this transition temperature reported in the literature. And Zhao Chen did a few things. So for instance, he looked at them as a function of sample type. That's important. We'll record this in the database. And it turns out that powder and crystal samples are slightly different, but they give noticeably better agreement between the respective values than thin film materials, which presumably have a larger variety in how they're processed. But if one looks into things a little bit more closely, one can also categorize this as a function of year. And it turns out that the early studies actually all sort of agreed when one could suspect that the run in the field wasn't yet there, and this was just an organic-inorganic compound. And then in the later studies, there's actually a significantly larger variety independent of sample type in what came out. And so this is something one has to be careful about, because now we're in this phase, and this is where most of the data that we have is generated. All right, so what's next? So we have a database, and we're growing it. And it's actually intended to be a community database with contributions from others, and it's open for this. Registration in this is free. And the idea is to have a carefully collected, curated database of data, our own or others in the literature. And the limit is finding enough people to curate data and putting them in. And it's also, in principle, designed to be incorporable and shareable with any interested larger material space. What it's not, at this point, is not a large data collection geared at uniformity of data, right? It's not supposed to have one type of data regardless of whether that method is appropriate or inappropriate. It's supposed to reflect the diversity of existing research efforts with some intelligence to make sure, and that means human intelligence often, to make sure that the data is actually trustworthy. And it's also not supposed to be a large standalone database that's intended to supplant everybody else. So if you go in, you find a list of contributors that have done something, but more importantly, you find the data contributors that are here. And as I said before, interestingly, the largest contributions really have come from some very motivated undergraduate students, which is really a pleasure to have worked with them. And I'm immensely grateful to them. The scope of the database I already mentioned in terms of materials and properties that are there. There's of course a lot of room for growth here, and the types of quantities that we collect are sample details. That's important. Synthesis is also something that we pay attention to. On the theory side, of course, we try to pay attention to what kind of computational methods was used. And then if you look, you find materials data that look hopefully as a database should be. This is one example of naphthyl methyl ammonium lead bromide. You find JMOL, which is a huge contribution to the community that this actually works in browsers. You can find information about crystal systems. You can actually verify data. So if you're registered in the database, you can actually verify somebody else's findings or raise a flag that the data might not be accurate. And you can also, for your own data, mint a DOI if you like to keep this permanently accessible. And those are just the larger images of what I just said, including references, including history of who extracted this. And there's other data. For this one, for instance, there's photoluminescence and the band structure computations that were done at a certain level of theory. So the other thing that came out of this and that I'm thinking might be useful for wider uptake is actually the software behind all these efforts. If you start this effort, one thing you find is that there's a lot of good open source software available that allows you to create a database in principle, but the actual data collection, you still have to program yourself. You have to create that from scratch. And so without Raoul Lasner, who's a full-fledged postdoc in electronic structure theory at the time, of course, and without Zhao Chengdu, who started this, as I mentioned, as an undergraduate, we would not be where we are, and the contributions of several other people. In fact, Matti Ropo on the first page is a collaborator who helped us a lot here. And so we put out the software that drives this database, which we call MatD3. So that's the software, not the data, as a separate publication, as an open source project that can be picked up by anybody else. So if you have a collection of data that you want to collect somewhere, the software here is there. It's based on the Django web framework. It deploys an SQL database, and it actually comes with an API for access and manipulation of the underlying data sets. And it's interoperable with a software called QResp that was produced by Julia Galli's group, which allows one to archive data in one's own papers. It also should be useful for many of the data efforts that we have in the world. And just to say that this MatD3 software is actually reasonably straightforward to install. So Yannick, one of the undergraduates on the first screen, did it on his own, on his laptop. It follows the usual Python paradigms, and then you basically install it by pip install. It has certain requirements for software that is needed. It also comes with tests, with unit tests, to make sure that the database actually works. And if that works out, if you follow this recipe, hopefully you have the database installed. The API is also reasonably easy to access by just using these entry points here that are documented on the web. And then finally, in the database itself, you have all sorts of properties, including compound names and IUPAC names, which is a story of its own. So we're trying to get IUPAC names for molecules correctly, and so this is a difficult task if you look into the details of how the IUPAC standard for organic compounds works. All right, and I mentioned these things before, in particular that you can verify data. You can of course download the data, and data sets can also be linked with one another in the MatD3 software to make sure that they correspond to the same measurement or reference. So what can we do? This is what I announced in my agenda earlier. So of course we can do something with the data, and here's something that we did ourselves. This was again led by Manoj Jana and David Mitzi's group with Rui Song, who's a PhD student in my group. And so in short, we were interested in the interplay of chirality in the organic components and spin splitting of the carrier levels in hybrid perovskites. And so this is just a short example of a chiral molecule, which is a mirror image that cannot be rotated onto itself. So it irrevocably breaks inversion symmetry in a structure, and therefore also the symmetry of spin bands in a structure. This is on the organic component. whereas often the semiconductor transport properties are more impacted by the inorganic components, so the octahedral inorganic groups that you see here in this example. And then the natural question arises that a lot of people are pursuing is, can we use chiral organics to control the spin properties of carriers? And then by spin properties, what I really mean is spin splitting of the band structure, so that carriers of one momentum have one type of spin polarization. In this case, the blue carriers of momentum, of negative momentum in this unit system are spin down carriers. And so there are different ways of breaking the spin symmetry. Here's Rashba splitting, which actually splits two separate bands if one makes a projection in their entirety. So we can try to find out about spin splitting. And it turns out if one uses a naphthol benzyl ammonium group in a bromide framework that's done in this particular material, and one uses only molecules of one chirality, one actually gets that spin splitting. I'll show you that in a moment. But more importantly, this can be related in detail to the chiral molecule imparting its structure onto the 2D perovskite layer. So the organic chiral molecule that's shown here creates some kind of helical in-plane distortion of the atoms in the inorganic plane. And that leads to a spin splitting that ultimately splits bands, as you can see here. So where you have spin degenerate bands in a centrosymmetric version, you'll have spin split bands in a non-centrosymmetric version of the system. And so this is the spin splitting that I'm talking about. You can clearly see this in the chiral versions of this material. But it doesn't appear in the racemic version. So if you have 50-50 mixture of NEA molecules in this case, then the bands are centrosymmetric, indicative of a centrosymmetric structure as they should be. All right, so this is interesting, but this is a single material and we studied it in detail. So for this purpose, the real question is, what can you do if you have more data? And so we have a little bit more data. And so Manoj went through a detailed analysis of 17 non-centrosymmetric chiral layered perovskite structures, including some that he synthesized himself to look at different characteristics of the structure. So octahedral distortions, but also bond angle distortions, and see what might be the driving force for this. And he also looked at 56 centrosymmetric ones for comparison. And it turns out that the driving force in this case was actually a fairly simple parameter that didn't need a great deep degree of machine learning. It actually went back to the foundations of the perovskite field, and then consisted of looking at different tilt angles between the octahedra that make up the inorganic structure. But this was not obvious to us in the beginning. So it's the difference between tilt angles on one side of a structure element like this and the other side of structure elements like that correlates most heavily with the spin splitting that we observe. And this really, in my view, is a success, because while we still have to make and characterize the structure, at least this gives us a direct indicator of where we should look for spin splitting in these materials. All right, so I'm heading towards the last part of my talk, and that really is about the question what to do next. And so this is in many respects something that if you know about materials data, you probably know about, but nevertheless it's where we'd like to go. So from the beginning of this project, we were in touch with Springer Materials. This was in fact always my concern, that we would collect a lot of data and then we would have it, and eventually the project would go away and the data would go away too. And so the sustainability question was on my mind, and I sent a letter email to Springer Materials before we even submitted the project, asking if they would be interested in collaborating with us, and they said yes, and sent us a letter of collaboration. And so it was always the plan, if we didn't have any other options, to work with Springer Materials and eventually incorporate the data that we could collect into their collection of materials properties. And so Springer Materials itself is a very big collection, as you probably know. It has all sorts of property types, all sorts of materials, 600,000 plus entries at this point of phase diagrams, structure, and properties of materials that you can access online. The history this, of course, goes back a long way. In fact, it goes back to Berlin, where apparently FAIR-DI is centered. So that's interesting. Berlin is still there, except at the time it was Landolt and Bernstein who founded the Landolt-Bernstein series. That was one of the critical drivers for this materials collection over many years, and with many very senior people in the community involved in this. Landolt-Bernstein apparently makes up still 30% of the material here, whereas 70% are made up of other databases that have been incorporated over time. And Landolt-Bernstein, for me personally, is of course of interest because, well, not of course, I did not mention this, but it turns out we actually got involved sideways a little bit, not directly related to hybrid organic, inorganic perovskites, but to help digitizing and reformatting the content of the semiconductor collection of Springer materials to make that ready for digital incorporation. So we did that for a few years, and other people in academia are also involved with Springer materials. So I'm not the only one on other volumes to work on Landolt-Bernstein data and make them digitally accessible. So you get from this format here to a MySQL format, and then eventually from the PDF format to something that is much more easily accessible as data in an interactive graph. And so in short, this is what we'd like to do with our hybrid cubed data as well as with other data related to perovskites in the future. That, however, is the future. And so this is the end of my talk. I talked fast. I'm sorry about this. That's the Zoom phenomenon, I suppose. The summary of this talk, what I wanted to emphasize is that hybrid organic, inorganic semiconductors are a rapidly growing material space that needs some categorization. We're trying this in the context of our hybrid cubed project. The details in these materials really do matter. So this isn't a simple plan of just putting something together and seeing whether it works. You need to pay attention to the atomic structure details, synthesis protocols, defects in the materials, and so on to get reproducible and reliable data. And so we're trying to do this. And the next step is to try and incorporate and grow this collection in collaboration with Springer materials. And in fact, there's a postdoctoral position open at Duke University to continue this work. If you're interested, contact me. Before I completely end, I would like to thank again the funding agencies, particularly NSF, who's funded our side of this effort for 4 years, for which we're immensely grateful, as well as Department of Energy, all the computational agencies, and Springer Nature. And with this, thanks again for having me, and thanks for your attention.
Thank you, Volker. So we have enough time for questions, which is definitely good for an interactive conference and community. So far, I don't see any hands up in the chat.
I have a small question here.
Oh, okay.
A live question for a non-live speaker.
Yeah.
It was an impressive overview of what you gave, and indeed I couldn't agree more with details matter, because over time, if you look, for instance, at detection of inversion symmetry, this is a very difficult crystallographic issue, and the possibilities of detecting this have changed over time. So the question is, if you curate data, how do you make sure that you make use of the most modern insights in all aspects that you mention, like crystallography, or in terms of other details as you mentioned them, the synthesis, it matters very much on which solvents you are using, on how you grow your materials. So how do you want to incorporate this into the curation of your database?
Yeah, that's a great question, because that's of course the reason why this here says postdoctoral position, right? And so I will say that my firm belief is that this actually takes care, and until we have a computer that can keep track of all the points you just said, which are exactly what's on my mind here, until we have a computer that can keep track of all these points, we're limited to understanding the science very well. And so the Landolt-Bernstein volumes, of course, were not edited by somebody who didn't have a different job. They were edited by people like Madelung or so, if I'm not mistaken. so people who were top scientists in their field, and they had the experience to do that. And I think the best we can hope for is to apply a lot of care to the curation that we do and read carefully. So that doesn't mean that we need to discount everything, right? So for instance, we can certainly and do have different data on the same topic from different sources in there, but eventually, if we're cautious, we can also identify particular data types as particularly reliable. But especially in the field of inversion symmetry, for instance, I cannot overemphasize the roles of David Mitzi and Manoj Jana, who I mentioned more, who are extremely careful scientists. And so they know what they're doing, and they pay attention to these issues in immense detail. And that's why we were ultimately successful, I think, with our study. But yeah, so this understanding that you mentioned is needed at the data level, and it takes somebody to actually bring in this understanding and make that work. I was lucky to work with a few people who actually had that, both the motivation and to do this, and they were not all postdocs, right? So Becca Lau, for instance, who I mentioned, and Zhao Chendu on the undergraduate side, and the others are also extremely careful in what they do, and so I was lucky to have them, but it's an ongoing challenge.
So it was Matthias first and then Gianmarco.
Actually, my question was somewhat similar to the previous one, but maybe I can then ask another question. Somewhat in the middle of your talk, when you discussed your calculations, which I think were HSE06 calculations. Mm-hmm. Now, when you talk about band gaps and band offsets, I mean, some people are fudging around with mixing parameters, which I never really liked very much. But I just wanted to know, actually, when it comes to so delicate questions as you are addressing, are you doing something there?
Great. So first of all, I think it's a totally, as you know, data-related question, because if you don't record these things, and we tried, at least I tried, whenever I look to record these things, if you don't record these things, you get random answers. So we stuck with one mixing parameter for the same reasons that you just mentioned, which is that I have concerns with, especially with the hybrid materials, with applying protocols depending on the material in question. Then one becomes very materials dependent. So I have another concern, which is that I know that the screening matters here, and the mixing parameter is an inadequate way, and in fact a non-adequate way of reflecting long-range screening in materials with two different components. But for the sizes we have, it's the best we can do. And so for this reason, for many years, I've actually written on this success here, and that was something we didn't take lightly, right? The fact that we predicted these band structures and their types, so different quantum well types for the lead chloride and lead bromide, lead iodide variants of this material. And that in a meeting, David Mitzi then said, this is very nice. The predictions look like my experiment in 1999. So we did not know this. And so we did a few more tests that I ironically left out in terms of time reasons. But for the qualitative, actually a few more papers with different people and different materials, that indicate that for the qualitative properties, our computational predictions are in line with what is found experimentally. But it took a paper with Letyan Du's group, who's also excellent at Purdue University, and a very detailed paper with Adrian Stiff-Roberts here at Duke and David Mitzi on 16 of these compounds. I might have thrown that into my supporting material. So we looked at predicted band offsets of 15 different perovskites of the type I just showed to look at the band offsets. And Adrienne actually synthesized a few of them in her lab, and they were then studied to convince ourselves this works. So in short, the answer is very detailed, because we actually try to do this and be cautious about our protocols.
Gianmarco?
Yes, so thank you. I very like the idea that you had to pay attention to the fact of what happens in case, you know, a project is not funded anymore. There's the notable example of the clean energy project, which has completely disappeared from the internet. And so, I mean, in the framework of Optimate, there was the idea to define something called necro-Optimate that allows to kind of revive some databases that were existing. In that framework also, I was wondering if in a sense, I mean, all these interfaces online are not replicating some tools to visualize the data. So you mentioned the Springer Materials interface, which is nice, but we know plenty of different you know, web interfaces, Nomad, Materials Project, and so on, where similar tools in the end are being developed. Have you never thought about, you know, some kind of standardization there as well?
Yeah, so as you know, I'm still quite interested in, so HybriD itself is not going away, right? So the database itself is not going to die. That, however, depends on external funding from funding agencies. And as you know, I'm quite interested in still getting the Optimate API in. In fact, I think this is limited by, sorry to go back so much, this is limited by the efforts of Yannick, one of our undergraduates who has actually programmed this and who had an interest in programming this. I personally think that the more widely data like this is archived, the better. And so a lot of our computational data, for instance, is in Nomad, and that's for a reason, because the Nomad database exists. I do think that the model of Landolt Bernstein, however, is a also compelling case that one should not forget. Right? It's actually the longevity of a publisher that made this possible. Right? And so it's something we should not quite discount. But and that's why I'm actually interested in supporting this as well, because I know that it's been around for a long time.
I mean,
so, yes.
My point was not to say that it's not interesting. The point is that is there in some way a way to share tools? So, for instance, there is the encyclopedia in Nomad that, in some sense, resembles also Landolt Bernstein, if you want. So maybe we may want to share some tools there at some stage.
Yeah, and this is probably more a question of how Springer Materials themselves, because I'm not Springer Materials, of course, right? I'm just a collaborator who's already happy that I'm a collaborator. But it may be a question to discuss with them. Yes, I agree.